Okay.
Okay, so welcome to CADEPS. So today we have Veronica Fantini, who is going to talk about L functions from fermionic traces of local P2. So, Veronica, please.
Thank you very much for the invitation. And yeah, today I will tell you about part of this joint project with Claudia Rella, and mostly these part of these two papers that are already on the arXiv. And so, as the title say, at some point we will see L function, but appearing from something that maybe you are not familiar with, which are the fermionic spectral trace for the geometry of local P2. So to begin with, let me start from the geometry, and then I will introduce also the fermionic traces and the L function, one after the other. And we are in the context of mirror symmetry, and as you might know, like one of the first and I think beautiful prediction of mirror symmetry, which goes back to the work of Candelas, De La Ossa, Green, and Parkas for the quintic threefold, is that if we want to compute the genus zero Gromov-Witten invariant of a Calabi Yau threefold X, this can be done looking at the periods of the mirror Calabi Yau. And by looking at the periods, I mean really solving a differential equation like the Picard-Fuchs equation. This relation between, this enumerative geometric data in genus zero, so number of rational curves and periods, can be also understood in the context of toric Calabi, when looking at the toric Calabi Yau threefold. Because in fact, in this example, the mirror can be described in a very easy way, in the sense that it is defined by the so-called family of mirror curves, which are typically of the following form. So they are curves in C star cross C star, and they are given by a function that I will denote O of x in this C star coordinate e to the x, e to the y. And typically this function is algebraic, but in fact is a polynomial that you can read from the toric diagram of the threefold. And it is a family parametrized by what I will call this kappa parameter, a parameter in the complex moduli of the mirror, meaning on the moduli space that parameterize complex structure on X check. So this is the description and how periods on this curve are related to the geometry to the enumerative geometry of X in genus zero. These happen in the following way. So if you consider a base of cycle for this curve sigma, then the coordinate Ti, which are the coordinate on the Kähler moduli, so the moduli space of X that parameterize Kähler forms on X, is proportional to the A period of this form lambda, which is essentially the one that you can read through the function O that defines the curve. And after taking a derivative, the generating function of the Gromov-Witten invariant is proportional to the B period. So in this sense, if you know how to compute the periods, and in particular, if you know how to solve the Picard-Fuchs equation for the mirror curve, then you can extract the geometric information encoded in the number of rational curve on the mirror using this type of relation. Of course, this is not the best way to compute the invariant. So if you are interested in the number of rational curves of degree 10 inside your toric threefold, you have a much better technique to do this computation. But I think conceptually, this correspondence between the coordinate in the moduli space and the generating function of the invariant on one hand and the period on the other hand, it's very interesting and is in a sense an instance of mirror symmetry. But now the natural question is what happens if instead of looking just at genus zero curve, we look at higher genus curve. In fact, higher genus Gromov-Witten invariant are naturally well defined on X on any toric threefold. But what is interesting is to understand whether we can find the analog of the Picard-Fuchs equation that allows us to compute this, which is related in some way with the generating function of this invariant. And we might have different way to answer this question. And in a very broad and maybe also vague sense, what I would just tell you is that the idea is to do a certain quantization. This is very vague. The point is that you might find different techniques also depending on the setup to quantize, and quantize might be done really in different ways. But what I want to, the only aspect that I want to stress through this quantization is related to the modular property of this function. So again, I'm not looking at computing the invariant one by one, but rather at understanding the property of this generating function. And one of the conjecture of Haganah, Bouchard, Clem, is that in fact this function f are a very nice modular property. They are quasi-modular function for a certain group in SL2Z. And the group is in fact related to the monodromy group of the Picard-Fuchs equation. And most importantly, here I'm not writing the explicit variable for fg, because in order to describe its modular property, we shouldn't take the t as I did before, but rather another choice of parameter in the complex moduli, which in this example is as a natural structure of an elliptic curve. So it's the quotient of the upper half plane by the group gamma. So this is the structure, what is expected in general for a certain family of threefold, and this conjecture has been proved in some example, for instance, for local P2. So let's look closer to the example of local P2. In this case, so what is local P2? First of all, is the total space of the canonical bundle of P2. So is this the total space of this privation over P2? And its mirror can be described again as I was writing before as a family of elliptic curve. In this case, as you see here, the function that before I was calling O of x, this polynomial, can be read from the polytope of P2, because here you see that there are the three axes. So the x-axis is responsible for the e to the x, the y for e to the y, and the other one for e to the minus x minus y. So this is the mirror curve, and the moduli space that parameterize the complex structure is given by this modular curve. So it's the upper half plane quotient by the group gamma 1, 3, and the group gamma 1, 3, I just recall here the definition. Okay, so as I was saying, the conjecture of Bouchard, Haganah, Bouchard, and Clem is a theorem in this case. And more precisely, if you consider the generating function fg of this Gromov-Witten invariant for local P2, then for genus greater than 2, as a function of a coordinate tau, which is defined in the following way, f is a quasi-modular function for the group gamma 1, 3. You don't have to remember the explicit formula. The point is that there is a special coordinate in the modular space that parameterizes complex structure. Is not the original kappa that you see here. Is tau, which is related in a sense to kappa and to t through the following expression. And what is relevant is that you have this modularity property for this generating function at fixed genus. Okay, so that's the part that I want to mention about the local P2 and somehow the geometry. And now let me introduce the fermionic traces. Here we slightly change framework. So the fermionic traces are introduced through a quantization And the quantization here is one of the simplest possible quantization you can think of if you start with a mirror curve. So in particular, if you start with a curve which was defined by the function O, you can quantize it, and these amounts of defining an operator that I will call it with this OX written in a slightly different way, which acts on function in L2 of R. And here these X and Y are two operators that do not commute. And in fact, the variable, the constant H bar that one has to introduce is precisely what measures the non-commutativity of X and Y. Now, so once you have this operator is not trace class. So if you consider its inverse, instead it is. And in particular, it means that it has a discrete spectrum. So if you want to describe the spectrum of the inverse of this operator, you can do it through this function that is called the spectral determinant, this xi, which depends on both kappa and h bar, and it is defined taking the determinant of this operator. Now, this function is entire in the parameter kappa and analytic in the parameter h bar. And so in particular, if you look at this expansion, the coefficient of the expansion at kappa equal to 0 are the so-called n-fermionic spectral traces. So the Zn that appear here are the trace. And here kappa is exactly the same kappa that you saw before in the definition of the curve. So it's again a parameter in the moduli space that parameterizes complex structure. So these are the traces, and they are defined from the quantization of the mirror curve. And how do they are related with the information or the geometry of local pitch of the original toric trifle? Well, this is has to be understood in the context of the so-called topological string spectral theory correspondence introduced by Gracia Sudamarino and Codesio Grassi Marino in this paper. And so the fermionic traces are like the part of the correspondence which is related to the spectral theory. They are related to somehow, they encode in a certain sense the spectrum of this operator given by the quantization of the curve. But they are related to the topological string side through the so-called, through this equation, which is here in yellow. And in particular, where the topological string side of the correspondence is encoded in this function J, which is called the total ground potential. So what this function J encodes, well, it is, I will not give you the definition explicitly, but it contains two contributions, what is called the worldsheet and the WKB. And the worldsheet is defined as a generating function of the so-called Gopakuma-Vafa invariant. So in a sense, this JWS is the one that encodes the counting, the real counting of genus G curves in the Calabi Yau, because the Gopakuma-Vafa invariant are integer invariant, while the Bromo-Witten are usually rational. So in this sense, this is really the actual count of this number of rational curve in X. And the WKB instead, it also contains a certain kind of invariant known as BPS invariant, but in a much more complicated way. And so it's better to refer to it as the function that contains it's expressed in terms of derivative of the Nekrasov-Shatansvili free energy. The point is that the function J is constructed, is like a natural quantity from the point of view of string theory, of topological string, and it contains somehow the invariant of the geometry. Notice that it is a function of two parameters, so not only of the moduli parameter of the Calabi Yau, which is through this relation, the mu, but it's also a function of GS, and GS is usually called the string coupling constant. But in fact, in this context, the string coupling constant and the variable of the quantization h bar are related by this expression. And sometimes I will use either one or the other to describe this, to denote this function. Okay, so these are the traces, and why we should be interested in this topological string spectral theory correspondence. Well, because one of the main problem, I would say, in topological string is that the natural quantity to study are this function, the so-called free energy, which are typically divergent. So you can only define them formally. Essentially, you take the generating function of the Gromov-Witten, what is inside this fg of t, but then you sum overall genera with this, and the string coupling constant is precisely the parameter that you introduce to keep track of the genera, of the various genus. Now, as I said, this is formal, but you would like to understand it as an actual function. So going beyond perturbation theory and understand it, so as we usually say, non-perturbatively. Or another way to say it, like to resum this function and produce an actual analytic function. Now, this is typically very hard, and there have been different progress in this direction. But if we want to study the resurgence or summability property of this function, looking at this formula, it's very complicated. So in the framework of the topological string and spectral theory correspondence, one attempt would be to think of this total string potential as the non-perturbative completion of the topological topological string free energy. And in fact, we already know that the function that I was called the JWS is, in a sense, the non-perturbative completion of the function f. Because if you know, for instance, as Gopakuma-Vafa invariant were first introduced, essentially they came as a rearranging or a resummation of this series where the variable gs get resummed into a certain sign function. And so, in a sense, this function, the generating function of the Gopakuma-Vafa invariant, can be thought of as a non-perturbative completion of this formal function. But the total string and potential is more general, so it has two contributions, not only the word sheet, so not only the Gopakuma-Vafa, it also contains the Nekrasov-Statashvili. And this is because we expect that... Yes?
Sorry, can I ask a question? I'm kind of confused with this GS notation. What is S exactly in the variable GS? Why are you
the variable GS is just keeping it's like sometimes people call it lambda. It's the variable that keep tracks of the genera when you want to define this function f. So you sum over all the genera the generating function of the Gromov-Witten.
Oh, okay.
Yeah, but when you write the G indices S, I mean, you don't use this a lot.
Sorry, no, GS is just one thing. It's not this G here is not the G of the genus. Yeah. Sorry, there are too many G. It's just a variable which is called GS.
So the S stands for what? I mean, why is S is there?
String. I think for string. It's like a notation.
String. Okay.
I think is string coupling constant GS. But I know that other people call it lambda. So maybe lambda is better because it doesn't create the confusion. It's just a formal parameter. Did I answer the question?
Yes. Thank
okay.
you.
Yeah, sorry. Okay, and so yeah, I was saying this the string and potential has the two contributions. So as the Gopakuma, but as also this Nekrasov-Statashvili part. And this is in fact is because in a sense it contains not just the non-perturbative contribution in the expansion GS at 0. So if you look at the series here, you can think of it as an expansion at small gs because it's in positive power of gs. The other one the J contains also the expansion in the other limit, which is a GS to infinity. So it's even more complicated in a sense. But since we know, since we have this conjecture of the TSST, we can try to understand and study this dual Lagrange potential, studying a slightly nicer function, which is the logarithm of the fermionic spectral trace. So let me just go back here. You have the relation between the two, which is a bit convoluted. What we would like to understand, so we would like to study the J, but in fact, it turned out to be much easier to study the Z, because being defined through this quantization, we can have explicit analytic formula for this Z. And so once we have them, we can study their asymptotic, their resurgence structure, and we will see which type of information we can understand. And this approach of studying the resurgence structure of these fermionic traces was initiated by Jay Gu and Marcos Marinho a couple of years ago, and then also by Claudia Rella in the example of local P2 and local F0. And now you see that here I'm talking about the limit at infinity at 0, because these are like the inverse with respect to the limit in GS. So let me just give you a very quick overview of which type of information we can get if we look at the logarithm of the asymptotic expansion of the logarithm of these traces. In both limits, they are expected to be divergent. So every time you get something divergent and so perturbatively, it makes sense to understand its non-perturbative correction. And in particular, the resurgence structure, which is a way to extract this non-perturbative correction, has been computed exactly in the work by Claudia. And in particular, she found out that the Stokes constant, which you should think of them as a sort of invariant associated to these traces, have a rich arithmetic structure. In particular, they are coefficient of Chuel function that will arrive at some point. And even more, this, as I said, this Stokes, you should think of this Stokes constant as a sort of invariant for the trace. But in fact, it has been conjectured by Gu and Marinho that they must have a geometric interpretation, and this in terms of the so-called BPS invariant in the limit h bar to infinity. Because the limit, so in particular, the limit that recover that should see the Nekrasov-Statasvili and not the Gromov-Witten invariant part. More than that, so in order to understand like the structure of this Stokes constant and whether or not we can understand the geometric interpretation, in the work with Claudia, we look at the generating function of the Stokes constant. And we try to understand what are the properties of the generating function. Well, it turned out that they are not, they are a very special type of modular form called quantum modular form. In fact, they are quantum modular function. But the surprise was to notice that they're quantum modular function for the group gamma 1, 3, which in a sense remember the geometry of the problem. Although here, I want to stress that the modular parameter for which these are quantum modular form is related to the h bar coordinate of the quantization. So it's not a coordinate, at least a priori, in the moduli space that parameterize the complex structure, because the trace do not depend on this choice. In a sense, the trace only depend on h bar. The dependence on the modular parameter has been, like put on a side after because it's like determine the coefficient of the parameter kappa. So the parameter kappa is kind of in the background. It doesn't enter exactly in the definition of the trace. But what we see is this type of modular property. And so what I would like to tell you now a bit with, of course, much more details is first give you a quick overview to what resurgence and quantum modularity are, and then see more in detail the example of local P2 But do you have a question?
No, that's okay.
It's okay. So let me start briefly with the resurgence and quantum modularity, because are the way we understand that we will see how the appearance of this L function. And I will start with quantum modularity. So quantum modular form were introduced by Daguerre some time ago, and his first definition was the following. So a function from the rational to C is a weight K quantum modular form if the co-cycle H, which is a function from the group gamma times R to C, defined essentially by the following difference, has better analytic property than the function f, meaning that is real analytic. So it extends over the real. It's real analytic everywhere up to this point for every element gamma. And here I just put a picture that I took from the paper, from the original paper of Daguerre, to give you an idea of what does it mean to be better behavior. So if you have a function defined over the rational, you can't hope for any analytic property. And so on the left-hand side, you see kind of the graph, the plot of the function f over a bunch of points for a specific example. On the right-hand side, you see instead the plot of the real and imaginary part of the function h. And so here you see that, in fact, it's much better behaved. It's defined over the real, and it has this nice graph. So you should really think of quantum modularity as a very, like a sort of minimal requirement for a function to be modular in some sense, but it's not quite modular. In fact, this function h is precisely what measures the failure of modularity. But the type of modular function that we will see today are in fact a bit better behaved, and these are what are known as holomorphic quantum modular form. These were also introduced by Daguerre, but the definition is only in one of these talks, so I didn't refer it here exactly, but you can see the exact reference in the paper. Now, instead of just considering a function over the rational, you look at a function defined on the upper half plane, an holomorphic function on the upper half plane. And now this, again, it's a holomorphic quantum modular if the co-cycle h, so the difference defined as before, has better analytic property of the original function. And now having better analytic property of a function defined on the upper half plane mean being analytic on a larger domain. And in this case, usually what is required is that the function is analytic on the complex plane minus and half ray. And typically we have to cut from minus dc to infinity, to minus infinity. So just and half line. Now,
I have a question.
Yes, sir?
Just as a curiosity, E2 would be an example of a holomorphic quantum modular form?
Yeah, exactly. Yes. And in fact, it's very special because E2, the co-cycle, it's gonna be a meromorphic function, just like one on like a y minus or cy minus d, cy plus d, something like that, right? So in that case, the co-cycle is a rational function. The failure of modularity is precisely measured by that. And I also have, thanks for your comment, because as I was also putting it as a remark, so the usual modular form, these are also examples of quantum modular form where the co-cycle is always zero because they are invariant. And in a sense, this quantum modular this family of holomorphic quantum modular form is huge because it contains really, I guess you can come up with many examples of them. I will give you some of them in next slide. The point is that it's a huge family, but the one that we can, we are trying to characterize through resurgence is a very specific family. So not all of them, not all quantum modular form will kind of fit in a sort of paradigm that we are proposing with Claudia. But I will explain it better at the end. So it's a very huge class of function. And let me give you some example. So let me just remind that the Q-Pokammer symbol is defined as the following infinite product. And I will usually think of Q as 2 pi e to the 2 pi I y, unless I say it differently. And now the first example I want to mention is this function f, which is a so-called quantum Jacobi form. So here I'm putting the adjective quantum to say that it's not, okay, a Jacobi form, but so it means that it will not be invariant, but the failure of this modularity is captured by the following function, capital phi, which is closely related to what is known as the Fader logarithm. But the point is that, I mean, one thing that you can see in this example is that if you are familiar with Jacobi form, you typically know that the invariance is given by acting with the gamma on both variable u and y. And here is precisely what's going on. If you see how this cocycle is defined, so how the difference, the failure of modularity is described, you see that you have these exponential terms here, which is responsible of the action of gamma on the parameter u. So the adjective quantum means is not anymore invariant, and the Jacobi, the part Jacobi form reminds you that it's almost like a Jacobi form, except that the invariance is broken. And this is an example given by Campbell-Wheeler in his thesis. But in fact, as a slightly less general example is given by the following function. So if you consider instead of this Q-Pokammer symbol, now you fix u to be a root of unity, like here, or you can also consider this other Pokammer symbol. Also, these are examples of quantum modular form, and this is like part of the joint project with an upcoming project with Claudia. And in particular, the example of local P2 will be a specific example of that one. So it will correspond to a specific choice of K and N, as we will see. But okay, so you have a family of quantum modular form that arise by this Pokammer symbol. But the most interesting one, probably the one that were also considered at the very beginning by Daguerre, were examples that comes from the theory of quantum invariance of free manifold and knots, or some class of Q-hypergeometric series. And among them, there are examples that are interesting because they are related to quantum to modular form. So, for instance, if you consider non-holomorphic Eichler integral of some partial theta series, and this typically happen if you look at some Kashaev invariant for torus knot, you find quantum modular form. But what is interesting is that the cocycle is expressed as an integral transform involving the partial theta series, which instead are modular, a usual modular form. And also, if you look at the Fourier series expansion of certain mass cusp form, again, these are quantum modular form, and the cocycle can be expressed as a function that involves the mass cusp form, which instead is modular. So sometimes you see this nice correspondence. So modular and quantum modular are kind of related, and these are very special type of quantum modular form. If you look at quantum modular form that arise from hyperbolic knot, in particular from the Kashaev invariant of hyperbolic knot, this is not typically the case, and the structure is more complicated. But I will not tell you much details in that direction. Just to tell you that this quantum modular form appear really in very different contexts. Okay. And so do you have question about this quantum modularity?
Maybe I can. In general, can we say that in the case of holomorphic quantum modular forms, do they have any Fourier series or not? In the case that the function, the correction, the H gamma is non-trivial.
Yes, if they have, so, yeah, typically the expansion is going to be a divergent series. So you can expand, but you will, in fact, find an asymptotic expansion. that's precisely the one feature of this function. So if you look at the expansion, if you want to, you are thinking in terms of like the Fourier expansion, right?
Yeah, yeah.
Is not going to be a Fourier expansion anymore because it's not going to be convergent, and it's typically asymptotic if you expand at minus d on c.
Okay.
Yeah, precisely. And that's why, since you get something divergent is why the theory of resurgence might help us to reconstruct it. So let's see what the theory of resurgence does, in fact. So a formal series, which is usually denoted of class Chevre 1, if its coefficient grow factorially fast. And in particular, if you have a function of this form and you want to understand its resurgent structure, the first step is to compute its Borel transform, because the Borel transform kill the divergence. And so in particular, you can go, it's a formal map that associates to a power series something that is convergent. In particular, if f is Gevrey, so if the coefficient grow factorially fast, you divide by factorial and you get something with a finite radius of convergence. Oops. And now the definition of resurgent that was introduced by Jean et Cal in the 80s is that a Gevrey series is resurgent if it has endless analytic continuation away for a certain set called the set of singularity. And the definition is a bit technical because, okay, it's what is written here, but let me just try to tell you in word what does it mean. So you start with your formal power series, which has this factorial growth. You divide by factorial, and so you get a germ of analytic function at the origin. This means that on this disk convergent, it might have some singularity. For instance, this orange point here. And now you want to understand if it's endless analytic continuable, meaning, okay, you want to do the analytic continuation and see if you can escape through the radius of convergence. And the series will be resurgent if in fact you can go behind the radius of convergent. And moving in the complex plane, you might see new singularity appearing elsewhere. And so the full set of singularity is just a set of points that you have to avoid. And the function that you are constructing might be super complicated and defined in a very convoluted Riemann surface. But that's the idea. If it's resurgent, the point is you can always escape and do the analytic continuation toward infinity. And the set of singularity might also be dense, but that's not a problem because the idea is that at each, the important point is that at each step, you only see finitely many singularity. And so you can escape. That's somehow the idea of resurgence. But why of the resurgent function? But why do we look at, like, why we are interested in this type of function? Because in fact, they have a very nice structure. And the structure is precisely the one that you can read from the singularity. So you start the analytic continuation of your function. And what does it mean? That if you see a singularity, then you go around the singularity and you extract more information. And this information is what is known as the resurgence structure. And its amount of the so-called Stokes constant and a new germ of analytic function, which are associated to the function. What does it mean? Oops, sorry. What does it mean? Let me just give you here an example. If the Borel transform of your function has a logarithmic branch cut singularity at the point omega, which means in particular that locally look like that. Now, you see that the Stokes constant and this what I call the new germ of analytic function can be read through the structure of the singularity. Essentially, if you do the analytic continuation, this logarithm is what will compensate the 2 pi I. And so the analytic continuation of this function around the singularity knows about the Stokes constant as this new formal power series attached to it. And you can also use this formal power series to now explore again the complex plane and see whether this function has itself other singularity somewhere else. So this is like somehow how you go and you can explore the Z plane, the zeta plane, to find more singularity. But even more simply, if your function has a simple pole at the point omega, in that case, the constant that you want to, the Stokes constant, the new information that is encoded at that singularity, is just the residue. And this will be the case for the example that we will see later on. So in particular, the only type of singularity we will encounter today will be simple pole. But that's somehow the general structure of singularities. And the point is really that near the singularity, you see more information. And now, why do you care about this more information? Because this is precisely what computes for you the non-perturbative correction. And in fact, the idea is the following. You start with your formal power series that assume it's resurgent. If its resurgence structure is given by the singularity omega, the Stokes constant, and this new series, then you can associate to that something which is non-perturbative. Non-perturbative because it has this exponentially small parameter. So this exponential factor here is something that in the limit y goes to 0 will disappear in a certain direction. And so it's what is invisible at the level of perturbation theory, but is what you can reconstruct if you study the resurgence structure of this series. And so this is typically the type of information we want to understand and compute when we study resurgence function. And is also typically the information that physicists are interested in, because it's what a priori they cannot have access to through the perturbation theory. And the function here, like phi tilde, is just formal. It's related to the lowercase phi. But sometime when we have more structure, we can actually produce an analytic function. So we can actually resum this series, not just finding this exponential factor, but really produce an analytic function using, for instance, Rella plus summation. But okay, so this is like the part I want to discuss in terms of resurgence. Do you have a question about that?
No, that's okay. Yeah.
Okay. And so now let's see in the example of local P2 a bit more detail. So the first fermionic spectral trace has this very nice expression that has been computed by Casciave and Marigno. And in fact, even for other Calabi Yau toric threefold, this integral structure is quite similar. But in this case, in the example of local P2, we also have this expression in terms of Q-Pocamer symbol. And what here I'm calling antilomorphic and holomorphic block is because here you see they are Q-Pocamer symbol, but with the Q tilde variable. And Q tilde is, it's related like not to H bar, but to 1 over H bar. For simplicity, I will just call the variable tau. And Q instead is the one related to H bar in this way. So you have both the dependence on H bar and 1 over H bar. And yes, the function that you see inside is the so-called Faddeev logarithm. In fact, also these Pocamer symbols can be rewritten in terms of a certain Faddeev logarithm, but we will see it at some point. Okay. So this is an analytic function in H bar. And its asymptotic expansion was computed by Claudia in both regimes. It's more convenient to look at the logarithm of this function. And as you see in the limit, both H bar to 0 and H bar to infinity, only one of the two blocks contribute. So maybe let me just go back. The antilomorphic block has Q tilde, so 1 over H bar. These only contribute in the limit H bar to infinity. And it's like vanishing at the limit H bar to 0, and vice versa for the other one. So here is like how the formal series look like. They are series with rational coefficient. This one here means Gevrey 1 as before. And here you see the coefficient written in terms of Bernoulli number and Bernoulli polynomials. And the structure of the two is kind of symmetric. I mean, they are not too different if you look at the two limit. And this symmetry between the two limits, we will see it frequently, like also in the next couple of slides. Indeed, let's see now the resurgence structure. So if you have this formal series, what is the resurgence structure? Is one of the most simple structure you might expect, because you only have simple poles which are displaced in this tower. So the distance here between two of these singularity is given by 4 pi square over 3. And the Stokes constant attached to this point, meaning the residue at this point, is given by this divisor sum function. And so in particular, thanks to that, you can see that the Stokes constant are the coefficient of a certain L function, which is the product of a Riemann zeta function and an L function associated to this character of modulo 3. So this is the non-principal character of modulo 3. And similarly, in the other limit, so if you look at the function psi, again, you have a tower of singularity. Now the distance between the singularity is slightly different, this 2 pi on 3. And the Stokes constant, so the residue, are now computed by this other divisor sum function. And the L function is defined in the following way. So you have a shift. If you look at the two L function, they kind of look the same. There is a shift in S, in the S variable here. Okay. Now, this is the resurgence structure. The non-perturbative contribution are the so-called, we sometimes call them discontinuity. The idea is that if you collect the residue, moving these two contours, one on the above the other, what you get is essentially a generating function of the Stokes constant, where the parameter that gives the generating function is given by the residue computation at this point. So it's an exponentially small parameter in the position of the singularity divided by h bar. And in the again, because we know this Stokes constant explicitly, this can be computed as a ratio of this Pochhammer symbol, where you see now the tilde because it's an inverse power of h bar. And this term, since it has the tilde, should also remind you of the anti-holomorphic block of the series. This zeta 3 is the third root of unity. So this is like closely related. The only difference is that here we have a 3. So essentially all the two Pochhammer are at a power 3, while before one was a power 2 and one was a power, let me go back. Here there was nothing and here it was a square. And now we have 3 on both. But they are kind of close. And similarly for the other series, if you look at the generating function, again, this discontinuity, so in a sense, the generating function of the Stokes constant, but in the sense of non-perturbative correction because of this exponential term, you recover something that look like the holomorphic block. So now this Q series with positive Q because they are exchanged. And so what we see, what we can expect from this analysis is that the non-perturbative correction, which is discontinuity in one limit, knows about the perturbative part of the other limit that survived in the other limit. So there is this kind of duality. And even more precisely, if we look at the quantum modular, if you now look at the quantum modular property of the generating function, where now I'm writing them function of y. So I'm sorry, because when I write them when I think of them in terms of discontinuity, I think of them in this inverse power of h bar or tau because they are the non-perturbative correction. In terms of generating function, I use a different coordinate y, which, okay, it's going to be related with the other two, but somehow is neutral in a certain sense. And so if we look at the function, if we define the function f0 and f infinity in the following way, again, by summing over the Stokes constant, the generating function is precisely what was written in the previous slide, but now with this new parameter q. And our main result in the two are essentially symmetric. Both generating function are holomorphic quantum modular form for the group gamma 1, 3. And the way we
Veronica, this is for local P2, no?
Yeah, this is only for local P2. I mean, I can tell you that we are now working for weighted project of local weighted projective spaces, which are a slightly generalization of local P2 because the trace has almost the same structure. So we still see this Pochamer symbol, but for instance, for local F0, where some numerical computation have been done, we don't have these quantum modular. We expected it, but we don't have a result yet. So this is only for local P2 so far. And in fact, we expected to see different group for different geometries. Okay, and so yes, in both cases, we have an holomorphic quantum modular function. I will tell you in a while, like a brief sketch of how we can prove this type of result, because at the end of the day, it only relies on the fact that this Pochamer symbol are quantum modular function. But the other point that I want to stress before we see the proof is that this group gamma 1, 3, I mean, I don't think it's a coincidence that it appears in this context, because it's kind of related to somehow the geometry of the problem, or at least it's the same group that express the quasi-modular property of the generating function of the Gromov-Witten, and in another way, it's also the same, I mean, it's the modular group for this modular curve. So although it's not the same thing on the nose, it might be related in some way, and this is what we are trying also to understand. But okay, so let's take a look at the proof, and I will just give it in one example because it's really symmetric in a sense. And so let's look at the example at 0. So in this case, let me define this function fr as the following combination of the two, f0 and f infinity. So the generating function of the Stokes in one regime and the generating function of the Stokes in the other regime. Why I'm doing that? Because as is written on the bottom, this function fr, capital Fr, is a ratio of Pochamer symbol. So I'm choosing this precise combination because it's I know that the final result is given by this ratio of Faddeev logarithm, and the Faddeev logarithm are holomorphic in the cut plane C minus the negative real. So this is what have the nice analytic property I'm looking for. And now let's take a look at the generator of the group gamma 1, 3. So these are these two matrices. And the function f0, as defined above, it's clearly invariant if you shift y by 1. Let me just go back to the definition one moment. It's defined in power series of e to the 2 pi I y. That's also why I choose y, because I get this invariance by t quite naturally from the definition. What is more interesting is the other cocycle, so the one that corresponds to the group element that I call gamma 3. And in fact, with respect to this element, so the cocycle is defined as the difference. And here you have no other factor because I'm saying our function, so weight is 0. If you look at this difference, now you can use essentially the definition of fr to replace this f0 by f infinity. If you do that, you get this function here. But now, and I do the same for the other f0, so I just change it in this way. But now what is interesting is that here, you can use the, again, invariance of f infinity for transformation y that goes in, y that goes in y plus 1, because it has the same invariance. And so these two cancel out. And sorry, now here there is something. These two cancel out. Maybe I put the wrong sign. I think so. Sorry, here maybe should have been different. But anyway, no, sorry, here I think there is something strange with this when I copied the formula, because F infinity, it's invariant, and I'm a bit confused why it doesn't go away. I think it should be, sorry, here I think there's a mistake. It should have been a minus, but I should double check in the paper. And the paper is correct, sorry. The point of the proof is that these two simplifies, and therefore, no, I think it's, sorry, this is a typo. This sign is a plus. Okay, anyway, because there was already the minus outside. So, okay, sorry. There is a typo here. Anyway, the two F infinity cancel out, and what you are left with is precisely what is written. So FR at this point and FR at Y. And as I said, this combination is just, it amounts to have this ratio of FADEV the logarithm, and therefore we know it's an holomorphic, and analytic in a much larger domain, which in particular proves that this function is a quantum modular form. And I mean, it was enough to check this property for the generator, because since H is a cocycle, then once you have it for the generator, you have it for all the other elements of the group. Okay, so that's the way the proof goes. And it's exactly the same in the other case for F infinity, as you can imagine. And now let me just mention very briefly something that we like summarizing all the symmetries that we have seen so far. Like, because I was keep telling you, we have these two limits that are kind of related to each other. So here is like the big picture that we gave, and in fact we explain that by saying it's a strong weak duality. Because if you start now with the discontinuity and you compute this asymptotic expansion, you get a certain divergence series. You can use the framework of resurgence and compute the discontinuity again. And the discontinuity are the anti-holomorphic blocks. So essentially what knows about what captured the perturbative expansion in the other limit. And you can close the diagram. And the fact that the diagram closed in this nice way, so that a priori was not guaranteed a priori from the structure of the function themselves, but in fact you can explain it in a very beautiful way, I think, using the functional equation that relates to the L function. And in fact, for the 12 function, after you complete them with defining lambda 0 and lambda infinity, you see that the functional equation is the following one. So it tells you that, in a sense, the analytic continuation of the L function for the Stokes constant in the limit h bar to 0 knows about the L function in the limit which contains the Stokes constant in the limit h bar to infinity. And I think this is quite, I mean, for me, was quite surprising. These L function are the one where you have the shift by S, of S by 1 in the Riemann zeta or in the Dirichlet L series associated to the character. But in fact, I mean, once you have this, since you are looking at the generating function, everything, it's really, all the structure that we have seen, that we have discussed through resurgence, it's really encoded in the functional equation. And the reason is because if you want to understand, if you think of this discontinuity roughly as a generating function of the Stokes, then looking at, so in particular as the generating function of the coefficient of the L function, computing the asymptotic is given by looking at the coefficient of the L function in negative integer, so at minus k. And then you need the functional equation to make sense of that. And since the functional equation is symmetric in this way, you see essentially the other type of discontinuity. So the other type of perturbative invariant. And even more, so this is like what we observe for local P2. But the same type of picture can be described more generally for other family of L function that kind of satisfy this type of symmetry. And this, in fact, is what we denote the so-called modular resurgent paradigm. So the idea is that if you start with an L function, now here plus or minus simply mean the Stokes constant, or like the coefficient of the L function for positive integer or for negative, labeled by positive integer or negative integer, but that's not very important. So if you start with an L function, you take its inverse Mellin transform, which gives you a Q series. And then by expanding the Q series, you find a divergent series. You can resum it, and you will find some some Stokes constant Sn. Now you can build an L function with this Stokes constant if they don't grow too fast. And this L function, you call it L0. Now you can repeat the same argument. So looking at the inverse Mellin, compute the asymptotic expansion, compute the resurgence. So compute in particular at the new Stokes constant. And if you look now at the L function was coefficient at the Stokes constant, you close the cycle. You go back to the original L function. And this is equivalent, so like moving along this rectangular is essentially equivalent to say that these two L functions were related by a functional equation like the one I showed you in the previous slide. So essentially the analytic continuation of one L function knows about the other. And this is like one example, but sometimes you don't see, there are other L functions that kind of fit in a much simpler version of this paradigm, in which the L function simply see itself. So once you go back to here, you don't see an L function with different coefficients, you see exactly the same L infinity. So you have a sort of triangle. And this, for instance, happens if you look at some Q hypergeometric function. In the paper with Claudia, we discussed the example of mass cusp form. So when you look at the Fourier series of certain mass cusp form, in that case, the paradigm is more simple. But it's kind of interesting, I think, the fact that the resurgence structure and this function f are related in this way. And the other important part is that, the other important comment I want to make is that now, if you try to understand which type of L function fit in this paradigm, well, you might try with just the L function of a modular form. So the inverse Mellin essentially is the Fourier expansion of the modular form. But in that case, if you took the asymptotic, you get 0 because it's modular. And therefore, this paradigm will be broken at this stage. You cannot, there is no resurgence to study, there is nothing. So in a certain sense, it's true that modular form are example of quantum modular form, but they don't really fit in this paradigm. This is something more special, and we expect to be able to prove that it's some special and it characterizes a certain class of quantum modular form. So in particular, the diagram goes as way when f infinity or f0 are quantum modular form. And the divergence is related to the divergence when you take the asymptotic. So the fact that in particular here you find something divergent seems related to the property of the function, to the property of the quantum modular form at the same time. You can think, I think you can look at both. So either we want to characterize L function which have a very special asymptotic, a very special functional equation or a very special asymptotics in a certain sense, because they produce this divergent series. Or similarly, we want to understand which class of quantum modular form fits in this paradigm, so comes from a certain type of L function. Okay, so that's somehow the idea of what I want to discuss. And let me quickly, oops, sorry, I'm a bit out of time. So let me just briefly sum up what I was saying. So we have seen that these there are usually L function appear in the context of modular form, but in the example I show you today, the coefficient of the L function L0 and infinity are the Stokes constant, and the generating function are quantum modular function. So the modular resurgent paradigm, which I just gave you in the last slide, is an attempt to understand and describe a certain class of quantum modular form based on the role of the L function and their functional equation. And the example of local P2, when we have seen the more complicated diagram with the strong and weak resurgence symmetry, is in fact an example of this modular resurgent paradigm. We are studying other example of Calabi Yau threefold, in which we would expect to see this strong weak symmetry, the new L function that satisfies this type of duality. And this is currently in progress with Claudia. So we are looking at local weighted projective space, and the local F0 is a bit more complicated because we don't have such a nice expression for the trace. So the computation from the resurgent point of view are a bit more are harder. And one way now that we have the result of quantum modularity, we are really at the very beginning, but we would like to see whether it can help to understand the geometric interpretation of the Stokes constant, which is what somehow the physicists are very interested in. And I think that having at least some arithmetic or some modular property, even though not exactly modular, could help at least in trying to compare this object and from a mathematical point of view, trying to understand whether they are related to each other. So thank you very much for your attention. I'll stop here.
Okay, thank you very much. So you